So the title of this dissertation is Magnitude and Mechanisms of Unforced Variability in Global Surface Temperature. So throughout this presentation, I'm going to be talking about global mean surface air temperature. So air temperature about 2 meters above the Earth's surface. And I'm going to be focusing on variability at the interdecadal timescale. So here's a time series at 200 years, and highlighted in red here would be variability at the interdecadal timescale. Now, you can imagine that global surface temperature can vary for a myriad of reasons, but a lot of the reasons that we're most familiar with tend to be considered forced variability on the system. So, for example, the sun's radiation can get more or less intense. Volcanoes can inject aerosols into the stratosphere, affecting the solar radiation that reaches the surface. Obviously, humans can contribute to the Earth's energy budget and thus temperature, but all these things are considered to be forced on the ocean atmosphere system. So this dissertation is concerned with unforced variability, which is the variability that simply emerges from the internal dynamics of the ocean atmosphere system. So kind of the quintessential example of that would be the El Nino-La Nina oscillation, which can affect global temperature. So I'm interested in the magnitude of unforced variability in global surface temperature. And I'm interested in the magnitude because this has large implications on the attribution of 20th century climate change as well as the predictability of 21st century climate change, both on interdecadal timescales. So let me just give you an example of what I mean here. So here is observed global mean surface temperature from 1880 to 2015. And we can imagine that if the blue line here is the forced component of variability, then that would mean that when we look back in time, most of the interdecadal variability that's observed is explained by forcings. And so what's left over, what's not explained by the blue line, would be the unforced variability. And that would mean that there's very little interdecadal unforced variability. So that has implications for future projections, because it would mean that if you knew the future projections pretty accurately, then you could essentially know what global temperature is going to do, because they're going to follow the forcings pretty diligently. Now we can imagine kind of another world where the dichotomy looks like this, where you have observations are the same in black, but this time the forced component of the variability is just a monotonically increasing trend here. So that would mean that all of the interdecadal variability that you see falls into the unforced component. So this means when you look back in time and you see some change in the rate of warming over time, you don't necessarily know if that's due to forcing or unforced variability. It would also mean that if you project into the future, your kind of confidence interval for where global temperature is going to be, even if you know exactly what the emission scenario is or what the forcing will be in the future, your confidence interval will be quite large, because you can still have kind of dramatic wanderings away from the forced response in the future. So for completeness here, I'll just put on a common estimate of this dichotomy between forced and unforced variability, where this is forced variability estimated by a group of climate models. And this would mean that the unforced variability is represented here, the variability that's not explained by the forcings. And so what I want to do is figure out the magnitude of unforced variability, so understand where we are on this spectrum. That's my first question. And then, of course, I want to understand mechanisms. So what modes of variability are responsible? What exactly is going on in the Earth system when you have a large change in global mean surface temperature? Where does the anomalous energy come from? So when you have an unforced warming event, temperature is essentially a measure of energy. So that would mean that the Earth system is creating an energy imbalance somewhere. And so I want to understand how that's working. How the restoring force works. So if temperature wanders away from its equilibrium value, what brings it back down towards kind of where it started? And then also I'm interested in how the magnitude and mechanisms of unforced variability will change as the baseline climate system gets warmer. So throughout this dissertation, I'm using a number of tools. So the primary tool that I use are coupled ocean atmosphere global climate models. And these are particularly useful for me because there are many climate model runs that are run under perpetual control conditions, meaning that there's no changes in external radiative forcing. So no changes in well-mixed greenhouse gases or solar radiation or volcanic eruptions. So all the variability that you see is by definition unforced, which makes it, of course, much easier to study. I also look at contemporary observations. So I look at the instrumental record of surface temperature changes that we've seen from the 1880s to present. I look at the satellite record of the Earth's energy budget, which goes from 2002 to present, as well as atmospheric reanalysis products, which are essentially weather models that assimilate observations into them over the historical period to give kind of a full, physically consistent picture of what's gone on in the past. And finally, I also use multi-proxy reconstructions of surface temperature over the past millennium to try to get an idea of how large unforced variability is. So getting at this first question of what is the magnitude, in a paper in 2015, we looked at the magnitude of unforced variability at the interdecadal timescale in as many climate models as we could get our hands on, as well as in contemporary instrumental observations. And so this is a plot showing 200 years of control runs from climate models, where I've ranked the variability from most variable in the top left to least variable in the bottom right. And you can see that there's a large range, and in fact, the most variable models are about 4 times more variable than the least variable models in terms of the temporal standard deviation of the interdecadal component here. And I can add on here 2 different estimates of what the unforced variability is in the observational record. And you can see that these estimates look actually quite different. So the phasing of the unforced variability differs here depending on how you remove the forced variability from the record. So we know, greenhouse gases have been increasing and aerosols have changed, et cetera, over the 20th century. And so that has to be removed before you can look at the unforced variability. And there's different ideas of how you should do that. And you can tell here that depending on your assumptions, you get a different answer. But what's interesting is that the magnitude of unforced variability between these 2 methods is actually almost identical. And these are ranked the same way that the models are ranked. So what this is showing is that 32 out of 34 models have less variability than the instrumental record would suggest, and only 2 models have more variability than the instrumental record would suggest. So the conclusion to this little portion here is that the instrumental record suggests that unforced interdecadal global temperature variability has a larger magnitude than that produced by most climate models. Now, since climate models are generally used to kind of inform the confidence intervals of how large unforced variability is, and if they underestimate unforced variability, then that means it might be valuable to derive unforced variability from another source to see if any of our kind of understanding of contemporary climate change would change if you were able to derive it from another source. So that's what we tried to do in this 2015 paper. We looked at reconstructions of surface temperature over the past millennium, and we tried to create a statistical model of unforced global temperature variability that then we could use to help us interpret contemporary observed trends in global temperature. So the basic idea of what we did is we looked at reconstructions, so from the year 1000 to 1850. This is an example of a reconstruction of global surface temperature. And here's another example, so you can see that there's a variety of estimates of how large the variability is. And here's 13 more examples. So we looked at 15 reconstructions total. And we wanted to figure out what the unforced variability was in these reconstructions. And so the first step was to remove the variability that was due to external forcings. So the relevant external forcings over that time period are forcings from volcanic eruptions. So these are two different estimates of the negative volcanic eruption aerosol forcing that you get over that time period. So there's also greenhouse gases varied over the time period. The amount of energy coming from the sun varied, and these are several estimates of solar radiative forcings, and you can tell that there's a large variety of estimates of how large solar variability was over that time period. And then land use change, so basically humans changing the surface albedo. So all these things contributed to the variability that you see in the reconstructions, and so that had to be statistically removed, and so we used multiple linear regression to remove that variability that was due to forcings from the reconstructions. And here's just an example of that, where the blue line is the original reconstruction of surface temperature, and then the black line is what's left after you statistically remove the variability that's due to forcings. So now we have this kind of estimate of unforced variability. And what we wanted to do was simulate this many times so we can put the kind of contemporary climate change into context. So what we did is we used autoregressive models to simulate the time series variability at a variety of timescales and come up with kind of an ensemble of realizations of unforced variability. So here's just one realization, one example of unforced variability over a 150-year time period. And then I'll just throw two more on here. And then I'll throw on the probability distribution of temperature at any given time for 15,000 simulations from this statistical model. And so now we can see from the 15,000 simulations, and these simulations sample uncertainty in the reconstructions and the forcing estimates over the time period. But we can see from this essentially the envelope of how large unforced variability is, at least based on the data that was put into the model. And this is useful because we can do things like take this envelope of unforced variability, tilt it upward, from 1900 to 2015, and then use this to kind of give us context for the observations that we saw over that time period. So we can throw in observations in here, and something that stands out here is that the way that I've set this up is that essentially the forced component of variability would be the black line. And so this is showing that the interdecadal rate change in the rate of global warming that we saw over the 20th century, so the strong warming from the 1900s to the 1940s, then a hiatus to the 1970s, then warming again essentially up to the present, that interdecadal variability does not necessarily require changes in the forced component of variability. And you could potentially get that just from unforced variability. That's essentially what this model is saying. So another way to say that is that unforced global temperature variability is large enough to have produced the observed interdecadal variability in the rate of warming over the 20th century. And then other things we can do with this model is, for example, we can look at the recent so-called hiatus in global temperature change. So it's barely even noticeable on this time scale, but if you fit a linear trend from 2002 to 2013 in the NASA GISTEMP observational record, you get a negative value, so a negative linear trend over that 11-year time span. And so we can use our model and to ask, how likely is something like that to occur? So what this plot is doing is it's looking at the probability of a negative trend of a given length from 1993 to 2050 over various radiative forcing scenarios. So if we look at RCP 6.0, which is kind of a middle-of-the-road radiative forcing increase through 2050, we see that there is a 70% chance of seeing at least one 11-year period with a negative linear trend over that time period from 1993 to 2050. So meaning that the so-called hiatus is not something that we should be surprised to see, and that's something that more or less we expect to come about just due to unforced variability alone. So moving on to our first question about the mechanisms of unforced variability. Our first question is, what modes of variability are responsible, meaning kind of what geographic locations are primarily driving global unforced variability. And this is motivated partially by a large disagreement in the literature, where there have been many papers that have suggested that the tropical Pacific region, so low frequency ENSO variability and or interdecadal Pacific oscillation variability, these modes are primarily responsible for driving unforced global temperature variability. So that's kind of one camp. But then there's a whole other group of papers that suggest that no, it's much more the North Atlantic that drives global temperature variability. So in this paper that I mentioned before from 2015, we looked at the regions that were most responsible for driving global temperature variability in both models and observations. And so here are maps of local temperature regressed against global mean temperature for climate models, and then observations in the red boxes here. And first I'll zoom in on observations. And as I mentioned before, there's multiple ways to remove the forced variability from the observations to isolate the unforced variability first, before you then do this regression to see where the unforced variability kind of originates from. But you can see that depending on how you remove the forcing, how you treat the forcing, you get a very different answer, where one way you get the North Atlantic as the primary driver, and another way you get the Pacific, kind of this IPO looking like pattern. So in this paper we kind of demonstrated why there was this disagreement in the literature. And it's hard to make a strict value judgment, but one of these methods, the one that gives you the North Atlantic, is essentially a naive type of detrending method, where this other method that gives you the Pacific as the primary driver of unforced global temperature variability, that method takes into account how forcings varied in space and time throughout the 20th century. And so I would say that the balance of evidence is on the more sophisticated method, or points towards the Pacific as being the primary driver of unforced global temperature variability, if you kind of had to make a call. And so then we can also look at what the models say. So you can see that from model to model there's a lot of differences. But one thing that we tried to do in this paper is identify what we called regions of significant influence, and those are stippled in the individual models here. And if you composite across all of the models and you just look pixel by pixel at which locations have the most regions of significant influence, which are regions that we've identified as primarily driving global temperature variability, there's a bullseye in the tropical Pacific, and there's much less of an emphasis on the North Atlantic. So it looks like climate models as well point to the Pacific over the North Atlantic. So overall, the balance of evidence favors modes in the Pacific over the North Atlantic as being the primary drivers of unforced global temperature variability. In the observations, it's the Pacific that stands out when you account for the spatiotemporal changes in forcings, when you're trying to remove the forced variability from the record. And in the models, there's a lot of disagreement from model to model, but overall, if you took a poll of the models, the Pacific would be more important than the North Atlantic. So moving on to our second mechanisms question of where does the anomalous energy come from. So this is something we looked at in a 2014 paper. And to set this up, I just want to think about temperature here in kind of the simplest way possible. So this equation just says a change in temperature of anything, essentially, is related to the flux of energy on that thing divided by the heat capacity of that thing. So when we're thinking about global mean surface air temperature, we can think about this equation as being applied to essentially the atmosphere plus the ocean's mixed layer plus the land surface. So when we think about it this way, we can think that the flux here can then be decomposed into a component at the top boundary of the system, so in this case the top of the atmosphere, which I'll refer to as N, and a flux component at the bottom boundary of the system, which I'll refer to as QBML, which BML just means bottom of mixed layer here. So we can think about these fluxes could vary potentially because of forced or unforced variability. And I want to point out that when contemporary temperature trends are discussed, it seems that certain categories of forced and unforced variability get emphasized more in terms of these fluxes. So you could imagine that, unforced variability could happen in net top of atmosphere energy imbalances. Unforced variability could happen in these QBML fluxes. Forced variability, of course, can happen regarding the net top of atmosphere energy budget. We don't usually talk about forced variability in terms of the flux between the mixed layer and the deeper ocean. That's usually considered to be a feedback. But of these three remaining categories, two get emphasized a lot more than another one. So to take the example of the recent disagreement between models and observations over the so-called hiatus time period, a number of papers have come out claiming that this is due to this NTOA component. But these have all essentially evoked forcings. They've all evoked forced N variability. So they've said something about how the solar radiation has changed in such a way, or volcanic stratospheric aerosol concentrations have changed in such a way that have caused this disagreement between models and observations. So they've emphasized forced net top of atmosphere energy budget variability. Now, unforced variability has also been a competing mechanism to explain the difference between climate models and observations over the beginning of the 20th century. But these have mostly focused on this QBML term. So there have been several papers that have come out claiming that, as models and observations have diverged here, more heat has been sequestered in the deep ocean due to internally generated changes in ocean circulation. So this component of the grid has also been heavily studied. So what I noticed is that what was often left out, just in general, in terms of talking about variability in global temperature, was the possibility of unforced imbalances in the net top of atmosphere energy budget. And so that's what this paper was essentially looking at. And it was looking at this in general, not so much in terms of the recent hiatus. I'm just using the hiatus as an example to show where the kind of literature tends to focus on. So in this paper, we used climate models. We used control runs from ocean atmosphere general circulation models. And I'm going to summarize the results in using a kind of cross-regression plot here. So this is like a cross-correlation, except I'm plotting linear regression coefficients against global mean temperature as a function of time lag, where on the left side we have linear regression coefficients that precede global temperature and time, and on the right side we have linear regression coefficients that follow global temperature and time. So first I'm plotting global temperature against itself. So the value goes to 1 at time lag 0, and then you're essentially seeing kind of an autocorrelation function here. So I will plot here the multi-model mean as well as the across-model standard deviation. So I'm compositing over the entire suite of models for this plot. So I'll put on here N, so the net top of atmosphere energy imbalance, which is positive downward. And we can see right away that as global temperature is kind of rising prior to its maximum, and you can think about, even though these are linear regression coefficients, you can think about this as basically like a composite of a time series. And if you explicitly make this plot in terms of composites, it looks almost identical. So we can think about this as the time period of increasing temperature prior to a maximum. This is a time period when N tends to be positive, meaning that the net top of atmosphere energy imbalance is contributing to the rise in temperature. And then as temperature is coming down on the right side here, N tends to be negative. And so what this means is that unforced global temperature variability is not only associated with the flux into and out of the mixed layer from the deeper ocean. And it also partially appears to be driven by N imbalances at the top of the atmosphere. And when you try to quantify this, it looks like that the N imbalances account for about 40 to 50% of the energy necessary to create the types of temperature changes that we're seeing. So it's not just that N imbalances contribute a little, they appear to contribute a substantial amount to the global temperature variability. So the next question we want to ask here is then, what causes this N variability? So going back to our diagram, you can imagine that the N component of variability can be further decomposed. So thinking about the radiation budget of the planet, we have the sun introducing shortwave radiation into the system. Part of that is reflected back to space from clouds. Another part of that is reflected back to space from the surface. And surface albedo can change in an unforced context due to changes in snow and ice. And then the Earth is emitting long-wave radiation, which interacts with water vapor in the atmosphere and interacts with clouds. And so these four components here can all vary due to unforced variability. Of course, the input to the system can't vary. That would be considered a forcing. But the rest of these can all vary. So we can look at how things change in terms of the cloud shortwave component, the clear sky shortwave component, the clear sky longwave component, and the cloud longwave component. So I'll take this N, and first I'll add in the longwave component, which we see is negative, so it essentially opposes the temperature variability. And then I'll add in the shortwave component, so that's positive, tends to enhance the temperature variability, and it leads it in time, showing that it partially drives the temperature variability. And then I'll split both of these into their shortwave and longwave components, or excuse me, their cloud and clear sky components. So now we have in blue solid is the clear sky, and in blue dotted is the cloudy sky. And then in red solid is the clear sky, and in red dotted is the cloudy sky. And we see that the three of these lines are positive, meaning that cloud and surface albedo enhance global temperature variability in this unforced context. And only one of the lines is negative. And so that negative line is what's essentially damping global temperature. And that brings us to our third mechanisms question, which is, how does the restoring force work? And this is a paper that we published earlier this year that looked at this in detail. And so there is a kind of expectation of what's going on here, and that is that we expect that as global temperature increases, the Earth gets warmer, and that's going to cause more outgoing long-wave radiation to space. So that is essentially described by what's called the Planck response, which is just the derivative of the Stefan-Boltzmann law with temperature, meaning that as a black body increases in temperature, it will throw more radiation, in this case, to space. So we do expect this to be here. And we can see from this time evolution that it is this Planck response in the clear sky long wave that eventually flips your positive energy balance to negative. So you have this clear sky short wave in the solid blue here that's kind of pulling N up, so that would be the surface albedo component. But eventually this one loses to the clear sky long wave, and the N sign flips. And so that's what's going to cause global temperature to then restore and go back to its kind of equilibrium value. But in this paper, we looked at this in a lot of detail, and we looked at various questions like where is the origin of the anomalous outgoing long wave radiation. And so I'll just kind of show a highlight from this paper where we broke down or we mapped these individual components of the top of atmosphere energy budget in space. And so you can see, for example, where the clear sky shortwave component, the positive values are largely coming from. So that's over the Southern Ocean where you're melting sea ice, over the Arctic Ocean where you're melting sea ice, and then over some continents where you have less land, snow, and ice. But then you can really see where this long wave damping originates from. And we can see that we have a lot of long wave damping in the long wave cloud component as well as the long wave clear sky component over the subtropical Pacific as well as Indonesia and the Indian Oceans. And so we found in this paper that part of the reason for that is you get this large scale atmospheric circulation change that causes drying of the atmosphere, so less water vapor, as well as less clouds in terms of cloud fraction, as well as lower clouds in terms of cloud height. And all of those help to increase the outgoing long wave radiation and thus essentially help increase the magnitude of the restoring force, bringing temperature back down to its equilibrium value. So one of the take-home messages there from that paper is outgoing long wave radiation, particularly over the western tropical and subtropical Pacific, so these regions, which is enhanced by atmospheric circulation changes when global temperature is warm, eventually becomes large enough to overwhelm the positive surface albedo feedbacks that you see in the shortwave clear sky component, and thus bring temperature back to its equilibrium state. So the third question then is, will the magnitude and mechanisms of unforced variability in global temperature change with warming? So this is a question that we looked at in a climate model context, and we took kind of one model and looked at it in great detail. So we looked at how unforced variability in global temperature was different between a pre-industrial control run and a 2 times CO2 control run, meaning that we doubled CO2 and let the system find a new equilibrium value and then looked at its unforced variability. So it's not in a transient warming state, it's just in a warmer state in the 2 times CO2 run. So going back to our previous diagram, you may recall that the shortwave clear sky component was the largest positive feedback on surface temperature change. And you can imagine that in a warmer climate, that might not be as effective. And that's because in a warmer climate, you reduce your climatological sea ice and your climatological extent of snow and ice on the surface of the planet. So this is a map of climatological change in the shortwave clear sky component after a doubling of CO2. And you see that, yeah, over the Arctic Ocean, over the Southern Ocean, over a lot of the continents, you get an increase since these fluxes are positive down. That just means a climatological melting of snow and ice. So essentially what happens is, without that snow and ice available to vary, that feedback becomes much less able to influence temperature. So you get a decrease in how large the clear sky shortwave feedback is, which then feeds into the net top of atmosphere energy budget, meaning that the entire net top of atmosphere energy contribution to global temperature change decreases in terms of its positive influence on that temperature change. So the result of that is that in the pre-industrial control run for this model, you have a large amount of variability, and this is, we looked at over 800 years of a control run. And so that you're looking at interdecadal to centennial scale variability here. And this variability decreases by quite a bit in the 2 times CO2 run, so it becomes much flatter. It's actually a 57% decrease in variability. So not only does the magnitude change, but because you're losing this sea ice, the kind of mechanisms of the variability change as well. So in the pre-industrial control run, here's local temperature regressed against global temperature. In the pre-industrial control run, most of that variability in global temperature was driven by these high latitudes, so driven by the Southern Ocean as well as the Arctic Ocean. Variability in those locations were primarily responsible for global temperature variability. Whereas in the 2 times CO2 run, where you've melted a lot of your sea ice, those areas no longer have the leverage to exert changes in global temperature variability. So the origin of that variability then becomes the North Atlantic Ocean in this particular model, which is interesting. So you have a fundamental change in the origin or the mechanisms of variability after warming, after you've gotten rid of that sea ice. So to summarize, the magnitude decreases and the mechanisms change due mostly to a reduction in climatological sea ice in this particular model. So going back over the questions that we've looked at, so what is the magnitude of unforced variability in global temperature? Well, it appears to be larger than most climate models simulate. And we see that in terms of both the instrumental record as well as reconstructions of temperature change over the past millennium. And so according to our statistical model based on reconstructions of surface temperature change, the magnitude is large enough to produce interdecadal global temperature swings like what we saw in the instrumental record without having to evoke external forcings. But that's not to say that external forcings did not contribute to what we saw. This is just saying that it could potentially be unforced variability responsible for that. So what are the mechanisms responsible? We looked at modes of variability. So in both observations and in models, it appears that the balance of evidence tends to highlight the Pacific, and in particular the tropical Pacific, as the primary driver of global temperature variability over the North Atlantic, where you kind of only get the North Atlantic in observations when you don't account for the spatiotemporal changes in forcings over the instrumental record. Where does the anomalous energy come from? Well, we found that unforced global temperature variability is not simply associated with the flux of energy between the ocean mixed layer and the deeper ocean, but it can also be partially driven by internally generated N imbalances or imbalances at the top of the atmosphere. So both in the cloud long wave and cloud short wave, as well as the clear sky short wave, these are all kind of enhancing global temperature variability. How does the restoring force work? Well, we found that outgoing long wave radiation, particularly over the western tropical and subtropical Pacific, which in this paper, but I didn't really go into, we found that that's largely enhanced by atmospheric circulations. This outgoing long wave radiation eventually becomes large enough to overwhelm these positive feedbacks from surface albedo and thus cause the N imbalance at the top of the atmosphere to flip from positive to negative and then restore the surface temperature back down to its kind of equilibrium value. And then finally, will the magnitude and mechanisms change with warming? Well, we found in one model in particular that the magnitude decreases substantially and the mechanisms actually are fundamentally altered in a warmer climate, largely because you reduce surface sea ice, which then eliminates kind of a principal feedback on unforced global mean surface temperature variability. So lastly, I'd just like to throw up some acknowledgments here. So my My primary advisor here at Duke has been Dr. Wenhong Lee, who I appreciate her service very much in that context. The rest of my thesis committee is Susan Lozier, Paul Baker, Drew Schindel, and Yi Ming. Other contributors to various papers that have come out of this dissertation are listed here. I want to thank Duke University in general, EOS faculty, staff, and fellow graduate students, funders, and then of course family. So my wife Heidi is here, as well as my mom, and then I have to mention our cat, Dr. Montenegro Vatush, who is not available to come today. But with that, I will take any questions. Thank you.